starboard software. Let me go out. Let me capture a picture of this particular thing. That way I can write on. Okay, so here you have this compound, and we've put it in our mass spec. Okay, now this compound itself has 48, and 9 is 57. That is 16 for 73, so its molar mass is approximately 74. And the question here is asking you, what fragments would these be? Now, the M means mass, the /Z means mass to charge ratio. Just read that as mass, because the charge is always positive 1. Okay? Just read that as mass. So in this compound, here's what it looks like. It has 9 hydrogens, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Excuse me. 1, 2, 3, 4, 5, 6, 7, 8. Where's the 9th one? Oh, thank you. Duh. I'm like, how come I don't have any more carbons? Okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to have a double bond. So I tell you what, why don't we do this as a practice thing? Given this structural formula, what possible compounds could we have? So if you see, when we're trying to apply the octet rule, it's a little funky. And that's part of this process, is we need to identify what type of compound this is. So let me clear some of these off. That would take a while with that little one, wouldn't it? Alright, and let's draw that thing. So it has 4 carbons. Now, if we had the OH group here, we'd see we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, pretty straightforward. I need one further. So this is one possibility. However, this group could be attached here or here. Well, or it could be here. That would be different. Agreed? We don't know if the OH group is here or here. Now, that's part of this technique, is identifying the actual makeup. But here's a possibility. Now, if this was the compound that we put in this particular spectrometer, and we blasted it into fragments, some of the fragments that we could form, now you're going to have to trust me on this, and here's what I would recommend you do. Separate carbons. It could separate it into this and this, and it probably will do so. So the fragments you would see here are this one, which is 15, and this one, which is 36, 52, 3, 4, 5, 6, 7, 8, 9. You probably see those fragments. It could separate it into those fragments. If it did so, you'd have 24, 25, 26, 27, 28, 29. And this one is 24, 40, 1, 2, 3, 4, 5. Hey, what do you know? See the 45 there? So that's the kind of process you'll have to go through. So in this compound, if you broke it into fragments, what would the masses of those fragments be? And we see a match here. So you're probably going to put that this fragment is most likely this one. You could draw that, or you could write the structural formula of it. That was pretty fast. Any questions on that? Here's what, and we'll do another sample in a second. Draw the compound as best you can. Smash it into fragments. Don't ever break off a hydrogen. That's pointless. There's going to be no fragment of 1. Nothing like that. Separate the carbons. Determine the mass of the fragments and compare that to the chart. And you'll see a match, or you won't see a match. If you don't see a match, then it means that fragment wasn't produced, indicating that's probably not the correct structure. Okay? Let's go ahead and go forward a little bit and see if I can find another example. Let's see. Yeah.
Would it break off just the OH?
Yes. So we've taken care of 2 of the. I gotta pause this again. Okay. So we've taken care of 2 of the techniques. We've taken care of infrared, which tells us what functional groups, mass spectroscopy, which tells us the mass and gives us clues as to what peaks are present. The third one, nuclear magnetic spectroscopy or resonance spectroscopy. This one is the most difficult in my opinion, only because it takes a little bit of organic stuff, so Karen should be the one teaching this one. Because she is the organic master. There's no doubt. Okay, so this technique allows us to determine, let me back up. Nuclear magnetic resonance spectroscopy detects hydrogens. How it works is irrelevant for this test. Does not matter. It detects hydrogens. How many and where they are. Okay? Now, as a very basic high school introduction to this, what it does is this machine, this device, detects where they are in relationship to each other. It detects unique hydrogens. Now, the only way I can make that more clear is to show you some examples. Okay? So we're going to start extremely simple with methane. It has 4 hydrogens. If you were to analyze this compound in a nuclear magnetic resonance spectroscopy device, chamber, whatever, an MR spectroscope, you would detect 4 identical signals. Because each of those hydrogens, their position relative to each other is the same. If we were to compare this result, this compound, to ethane, now this hydrogen and this hydrogen and this hydrogen would show 1 peak. This hydrogen, and this hydrogen would each show a peak each. But because they are relatively the same, their location is the same. Or in other words, this hydrogen is attached to a carbon, which is attached to a CH3 group. This hydrogen is attached to a carbon, which is attached to a carbon CH3 group. This hydrogen is attached to a carbon attached to a CH3 group. This hydrogen is attached to a carbon attached to a CH3 group. This hydrogen is attached... Do you get the pattern? The pattern. What I'm trying to say to you is their chemical environment is the same. Remember, do you guys remember why on your test that you took today, the paper 1 or paper 2, why are average bond enthalpies not good uses for determining the enthalpy of a reaction? Because they're averages. They are influenced by their environment, right? That's what this is detecting. The environment that the hydrogen is located in. If their environments, if their surroundings are equivalent, it shows the same peak. However, if I showed you this compound, now we've got a difference. Because now we've changed this molecule. It's got a different functional group. Oxygen has a different electronegativity. It's causing electrons to behave differently all around it. Not just in the bonds adjacent to it, but all around it. So here, I would see 1 peak indicative of these hydrogens, because each of them could be described identically. This hydrogen is attached to a carbon attached to this mess. This hydrogen is attached to a carbon attached to the same mess. This hydrogen is attached to a carbon attached to the same mess. Hence, they would all show the same peak. Do you understand? This hydrogen is attached to a carbon, which is attached to a methyl group and OH on the other side. This hydrogen is attached to a carbon attached to a methyl group and OH on the other side. So this would be another peak. They have the same environment. This hydrogen would be yet another peak. The same environment. You understand? 3 different peaks. Does everyone understand that? Mm-hmm. Now the location of the peak on the printout, and I'll show you one in a second, is on a basically think of it as an XY plot. Okay? And on the X we call it chemical shift. And you can see that's the column we see here. This is from your data book, so you'll have this chart available. And it usually starts with a reference point. It's called 0. It's not important what it is. There's a reference point over here. So the number here is in reference to that as the 0 point. And on the x-axis is the number of hydrogens. Think of it that way. That's not the technical label for the axis, but that's good enough for us. So what we would see here, and this is important, we would see 1 peak for this. Now, you can see that group. I know it's very small, and I'm sorry. I'm going to try and find it I don't see it's probably even further down. There it is right there. I know you can't see it, but I'm showing you right here. So we would see a peak somewhere in the range of 4 to 12 for this. That's very high. So I'm going to use that peak here. This is that OH group, that hydrogen as part of that OH. Remember, it's just the hydrogen. Now here we have CH2 next to a hydroxyl group. I'm going to guess it's somewhere in this area. It doesn't matter. But now here's what I want to show you. I'm sorry. That was weird. It's twice as high. This one, I'll number these. Why do you think this line is twice as high? There's 2 hydrogens. Relative to this one, there's twice as many. If this line here indicates these hydrogens, notice, further from the more electronegative elements, the closer to 0 it is. That's a trend you'll see. How high will this line be? That's what an HNMR spectrum does. It gives you clues to structure, because a sign, 3 hydrogens that are the same is very indicative of a methyl, a CH3 attachment. Does that make sense? Yeah.
So you're always like graphing from the perspective of the hydrogens?
We are graphing the hydrogens.
Okay.
Yes.
It's always the hydrogen.
Yes. That's what it's for. It's not important how it works,
Okay.
but yes, the size of the peaks represents the relative number of unique hydrogens. And when I say unique, I mean in their chemical environment. Is that good? Make sense? Okay. Let's go ahead and jump back out and see if we can find one that takes advantage of this. Let's see. Okay, so here's one.